mathematical modeling of Elbrus Glaciers in the 21st century. Presenter is Постникова Таисия Николаевна.
I will talk about numerical experiments conducted to predict the future configurations of the Elbrus glaciers for different climate scenarios. Elbrus is the highest peak in Europe. It is a dormant volcano, currently covered by around 30 glaciers. It belongs to the Central Caucasus, and the glaciers of Elbrus belong to two river basins, Terek and Kubань. Our previous research was focused on all the glaciers of these river basins, namely the whole Northern Caucasus. And this research showed that under the warmest climate change scenarios, almost all the remaining ice mass in the Northern Caucasus will be concentrated on Elbrus by the end of the century. Hence, it is interesting to focus on Elbrus glaciers separately. Here, 13 of the largest Elbrus glaciers are labeled by numbers, and the glacier boundaries are drawn for the year 2000 and are based on the Randolph Glacier Inventory 6. And here in brown, you can see the debris cover of the glaciers. And to the right, you can see the satellite image from 2023. The glacier hypsometry data for the model were obtained from Farinotti et al. 2019. And in general, these data agree well with the data obtained from radio sounding by Kutuzov et al. 2019. And both studies share an interesting feature, a very thick ice plateau under of Zekollari glacier. And to the right, you can see the elevation change of the Elbrus glaciers from 2000 to 2020, and this data is used to calibrate the mass balance module, which I will talk about a bit below. And through modeling, we attempted to answer the following questions. What will be the geometry of the Elbrus glaciers in the future? Then, when is the likely formation of new proglacial lakes, retreating glaciers, and in which areas the lakes could be dammed by the dead ice? So the glacier model usually consists of two main modules. First is the module where the glacier-atmosphere interaction is described. So here we calculate glacier accumulation from the snow precipitation and ablation from temperature, and usually the full mass balance module is meant to use the radiation components, but our model is simplified, and melt depends only on positive temperatures. Second, there is a transport from the accumulation area to the ablation area. This is the dynamic model. And these two modules are connected through the mass conservation law, which is written here in the first equation, which is described along the flow line of the glacier. So this is not a 3D model. It is a kind of approximation. And here the change in ice thickness is explained by ice flow and by mass balance B. So this is the prognostic equation, which means that if we know the state of the glacier now, if we calculate its glacier's velocities, and if we know the glacier thickness now, we can calculate the glacier thickness change and the glacier geometry in the future. And the first two modules are borrowed from the previously existed Glowjam flow model. And in addition, we added a module for the evolution of debris cover. The debris cover is essentially a layer of sediments that reach the glacier surface through various processes, such as the melt-out of basal sediments or erosion of slopes and avalanches. Sediments can be buried by snow, transported inside the ice, and melt out in the ablation area. Since the sediment material is transported downstream along the glacier, its evolution depends on the distribution of velocities on the glacier, and the debris model is therefore linked to the dynamic module, and also the debris cover module linked to the mass balance module, because the more a glacier melt and the larger becomes the ablation area, the more debris cover melts out. And since the debris cover plays a crucial role in regulating glacier melting processes, we know that thin debris cover or scattered small particles on the glacier accelerates melting because they have lower albedo, but a debris layer thicker than a few centimeters suppresses melting up to complete isolation. Therefore, the mass balance module also depends on the debris cover. And so the climate scenarios from the climate model intercomparison project, CMIP6, were used for future climate changes, and the calculations of glacier volume change, which we calculated for the whole Elbrus, show that the volume of Elbrus glaciers will decrease almost linearly until 2040, but then slow down as the glaciers reach new equilibrium and retreat to higher elevations. And until 2060, the glaciers could reach equilibrium with the climate under moderate warming, the blue climate scenarios, and possibly by the very end of the century, if we use the medium climate scenario in yellow, and ice can mostly retreat to the very top under the most aggressive climate scenarios. According to our projections, the average annual mass reduction rate will double the next 20 years compared to the previous 20 years, with the greatest mass loss projected for the Zekollari glacier. But in the future, until the end of 2070s, we can see that the mass loss approaches contemporary levels. On the mass balance plot for Elbrus as a whole, we can see that the mass loss per year will increase roughly until 2035, and then as glaciers retreat further up, it may decrease slightly for warm scenarios and drop to zero for more moderate scenarios. As for the debris cover, it does not play a significant role in calculating overall glacier volume changes. However, it can locally affect the preservation of newly formed dead ice areas beneath it. Dead ice areas are the areas which are not connected to the active glacier. They can be preserved under the debris cover when glacier retreats up, and these dead ice areas can slowly melt and create circumstances for outburst floods if these areas create lake dams, etc. Here we can see the profile of the Küçükürklü glacier. On the left, when we don't use the debris evolution module, and to the right, when we use the debris evolution module, and we can see that the different pattern of glacier retreat. So the glacier retreat is slower when we consider debris cover until 2030. 2030, and we can see that after 2030, a small dead ice area is preserved under debris cover, while if we don't include debris cover evolution, we don't see this dead ice area. So this is important to consider if we want to project dead ice area formation. And in the work of Lavrentiev et al., 2020, places of over-deepenings were identified where the existence of lakes is possible in the absence of glaciers on Эльбрус. They are located beneath the glaciers of Большой Азау, Улучеран, Терскол, Карачаул, Горбаши, and Zekollari. Some retreating glaciers covered by debris cover will leave behind dead ice areas that can dam these glacial lakes. And the numerical experiments allowed the calculation of the formation time of glacial lakes and an assessment of whether the formed lakes will be dammed by dead ice areas, potentially increasing the risk of their breakthrough. Here, the 10-year snapshots of Elbrus glacier configurations are presented under moderate warming. The largest lakes, located below an elevation of 3,500 meters, form around 2030s, 2040s, regardless of the climate scenario. Possible uncertainties may thus be mainly related to simplifications adopted in the model. And also, it's interesting to see that the Kükürtlü Glacier periodically advances and retreats after 2050. When we examine the modeling results in 2020, we can see that areas of dead ice are forming near the Zekollari glaciers, so today, and lake number 5 is taking shape. This aligns with the recent studies by the Kukin et al. 2022, which have shown that currently in the location of the retreating glacier, Zekollari, a series of lakes has emerged. Some of them are dammed by the dead ice, making this area a source of potential outburst floods. And 15 years later, by approximately 2035, but with like 10 years uncertainty at least, the Zekollari plateau becomes divided into an active glacier and a dead ice area up to 60 meters thick. And this dead ice can persist over 10 years and act as a dam for a large lake at the location where the plateau once existed. However, we don't know geomorphological setting under the glacier, such as how efficient can be the water drainage which can form from this lake, and this adds to our modeling uncertainties. Also, we can note that around this time, the Большой Азау glacier is roughly divided into 2 glaciers as well. So, by the end of the century, under moderate warming, the positions of glacier fronts stabilize. Local depressions located above 3,500 meters may turn into lakes after 2050, and the main source of uncertainty in this case is the climate scenario, with the uncertainty increasing over time. With the maximum warming, glaciers on Mount Elbrus may recede above 4,000 meters above sea level, and up to 17 new lakes are likely to form in this place, and other depressions will remain ice-covered. And I will not go into the conclusions again. I would just point out that before 2050, the main uncertainty source is the input data and modeling simplifications. So in the future, I would prefer to use more precise input data for the topography of the ice bed and from the maybe the 3D model of ice dynamics. Yeah, thank you for the attention.